organizando el live streaming.
Vale, ahora sí, cuando queráis.
Okay, so welcome everyone. So we're happy that you come here to this seminar on the occasion of the Asteroid Day, and especially because there will be no pizza at the end, so it's great that you're here, even without that. And welcome everyone at home also following this this talk that will be today by Josep Trigo about the DART mission. Today it's celebrated around the world, the Asteroid Day, which is celebrated since 2015, every June 30th, because it's the anniversary of this Tunguska event that happened in Russia in 1908, which is one of the largest, let's say, the largest impact that we have in recent history. And we're quite happy that we have this talk today and these announcements from by Josep Trigo. We don't need to do, you all know him. We don't need to do like a long introduction, but he's a tenure scientist from CSIC since 2009. He's also the leader of the research group here in the institute about let me see if I say this right, meteoroids, minor bodies, and yes, and then so he's also a leader on these topics. And apart from that, he's really active in outreach activities with many public talks organized, different blogs he's running before in Investigación en Ciencia, now in the conversation that are very popular. And he's also the leader of the Spanish Meteor Network, this pro amateur group that it's very active, and he's also will tell us a bit about that now. Okay, welcome, Josep Maria.
Okay. Thank you, Jorge. Thanks to the Institute of Space Sciences, CSIC, for giving us support over the years since my return from UCLA in California, where we were learning all the time. Young scientists, we are learning on meteorites and well, these exciting topics that we still don't understand very well. You know, this talk, I will apologize for people looking for the talk in English for a few minutes, because I will also speak in Catalan and Spanish. But be ready, because at the end, I will give the talk in English. The same talk will be given for the Planetario de Bogotá tonight at 23 hours CEST in Europe, in Spanish. And then I think is everything covered. I will plan to contact as well in the Asteroid Day in Nicaragua at mid-afternoon. So it's a very exciting day for us with all these announcements, with a lot of interest. And I'm very glad, and I thank all people that is not here, even close to me, you know, in this screen, because has made over the years, well, a passion, my own passion on the understanding of, you know, the things that are reaching us from the cosmos. They are reaching the surface of the Earth as meteorites and other things. And then I will change for a few minutes to Catalan and Spanish. Bueno, bienvenidos todos. Hoy voy a haceros una presentación que espero que os guste, particularmente describiendo pues lo que es la nueva. Vamos a ver si podemos. Sí. Vamos a ver si lo podemos. problema es que no puedo pasar la pantalla. Ni la veo. Es que yo no lo veo así. Entonces, estoy duplicado, sí.
¿Ahora cómo se ve?
Ahora. Vale, muy bien. Bueno, gracias, Jorge. Bueno, pues vamos a presentar una nueva sección de la web del Instituto de Ciencias del Espacio, del CSIC, que se llama Citizen Science. Pues este apartado pues nos va a explicar que, bueno, la idea es buscar la cooperación de los jóvenes y no tan jóvenes que tengan interés en estudiar estos fenómenos y que, bueno, en principio habrá dos apartados importantes. Por un lado, continuar los 27 años de existencia de esta red de investigación sobre bólidos y meteoritos, que tiene varios objetivos científicos de primer calibre y es fuente, pienso yo, de búsqueda siempre que hay algún evento inesperado en el cielo. Y estamos hemos podido recuperar 3 meteoritos y, bueno, caracterizar estas rocas en primicia, estas rocas caídas en España. Muy bien. Entonces, en este caso, pues voy a presentaros que esto es un proyecto multidisciplinario en el que colaboran pues aficionados y profesionales de toda España y en el que evidentemente estamos colaborando con centros de todo el mundo. Presentamos este listado de bólidos de la red de SPMN CSIC, donde ya ahora mismo y a través de la página web del instituto se pueden comprobar cada uno de estos últimos eventos y se puede acceder a los listados de años anteriores. Históricamente yo fui pues, profesor asociado de la Universidad Jaume I de Castellón y entonces a los listados de años anteriores están almacenados en esa web en concreto y bueno, son también accesibles. En esta página de Ciencia Ciudadana también tenemos vídeos, acceso a vídeos de reconstrucción de trayectorias, de órbitas, de los últimos meteoritos que hemos estudiado, las últimas caídas de meteoritos. También se puede acceder a dónde tenemos estas estaciones en colaboración con centros de investigación de toda España y también con muchos astrónomos aficionados y astrónomas. Y por poner, no sé por qué, perdonad, aquí, bueno, mencionar algunas de las estaciones de detección operativas que tenemos en muchos puntos de la península, en Baleares y Canarias. Bueno, pues todas estas colaboradores que a lo largo del tiempo pues no han cesado de enviarnos información y responder. Tenemos un listado al que una lista de correo en la que todo el mundo puede contribuir con sus propias detecciones y de esa manera buscamos contrapartidas en diferentes puntos de España. Y registramos un área, un volumen atmosférico enorme, porque os podéis imaginar, no solo controlamos la España peninsular, sino tenemos también cámaras en Baleares y también cámaras en las Islas Canarias, con lo cual este es un reto del máximo calibre, porque estamos hablando de, bueno, decenas de bólidos al mes y entre los cuales el objetivo, ¿cuál es? Bueno, pues evidentemente reconstruir trayectorias, órbitas en el sistema solar y sobre todo, muy importante, identificar cuáles de estos bólidos sea ahora o quizás en el futuro, hayan producido meteoritos, porque nuestro objetivo primordial es recuperar meteoritos frescos, y de esa manera poder comprenderlos y analizarlos y estudiarlos en primicia, que nuestros estudiantes tengan acceso a material de primera línea. Y, por supuesto, preservarlos, porque este es el objetivo. Los meteoritos en España, desde el año 2007, conseguimos que fueran reconocidos como patrimonio geológico. Entonces, los meteoritos caídos aquí se deben preservar y deben estar accesibles tanto a museos para su preservación como para centros de investigación para su estudio y caracterización científica. Bueno, aquí estoy pasando algunos de los centros que colaboran con nosotros, y hay de todo tipo. Bueno, por brevedad, pues no voy a citar todo el mundo. Aquí tenemos, por ejemplo, el grupo de bólidos de la Universidad Complutense de Madrid con el profesor Jaime Izquierdo y el doctor Jaime Zamorano. Bueno, hay aficionados pues con un entusiasmo como pueden ser David Molner, que opera 3 estaciones aquí en Cataluña, tanto en Breda, San Celoni como en Blanes. También Antonio Robles, que opera una en Sevilla, Carlos Alcaraz en Corbera de Llobregat, Diego Rodríguez en Collado Villalba y, por ejemplo, en Canarias tenemos la labor impresionante de Ramón López, Stargazer Lanzarote, desde Lanzarote, a la que se ha unido recientemente Francisco Grande desde Gran Canaria, y también tenemos un astrofotógrafo, bueno, pues maravilloso, que hace las maravillas en estas imágenes All Sky, se llama Enol Matilla y está en el Tablero, en Tenerife. Y este es un proyecto abierto a todo el mundo, evidentemente, porque lo único que se necesita es captar el cielo con cámaras y, por tanto, pues obtener estos registros. Recientemente firmamos también un convenio de colaboración con el Observatorio de Pujalt y estamos trabajando con ellos en estas imágenes de todo el cielo para tener un control exhaustivo de estos fenómenos que son súbitos. ¿Y por qué son súbitos? Porque básicamente son rocas de menos de 1 metro, por término general. A veces hay pequeños asteroides de pocos metros. Ya hemos detectado 7 pequeños asteroides justo antes, en forma de asteroide moviéndose entre las estrellas con nuestros telescopios, justo antes de impactar contra la Tierra. El primer evento ocurrió del 2008 TC3, un asteroide que en solo 20 horas cayó sobre Sudán y produjo una bola de fuego, y luego se recuperaron. El doctor Peter Jenskens de NASA Ames pues recuperó meteoritos en colaboración con la Universidad de Sudán. Y recuperar meteoritos de estos asteroides que impactan es científicamente de gran relevancia. Aquí paso, bueno, algunas asociaciones, la Agrupación Astronómica de Sabadell, la Agrupación Astronómica de Teruel, bueno, y muchas otras que no voy a citar, pero que obviamente hacen un trabajo continuo. Estamos codo a codo, cada día carteándonos, enviándonos datos para hacer posible, pues precisamente este listado de bólidos que está accesible y que nos permite precisamente identificar aquellos casos que necesitamos estudiar en más detalle y, evidentemente, modelar estos procesos de caída de estas bolas de fuego, aplicar un perfil de vientos cuando comienza el vuelo oscuro, cuando dejan de ser luminosos, para ver hasta dónde derivan esos meteoritos, ¿no? Esto, evidentemente, es un reto de primera magnitud y pues requiere un esfuerzo adicional que muchas veces no se ve, pero bueno, lo importante es que estamos ahí y seguimos con esta pasión por conocer lo que llega del cielo. Y así nos embarcamos en un nuevo proyecto que esperamos tenga pues salida y sobre todo podamos seleccionar unos cuantos institutos para que estudiantes de eso pues aprendan a ser jóvenes científicos y nos ayuden a recuperar micrometeoritos. Porque un colega que estuvo aquí con nosotros, una persona muy cercana, John Larsen, seguramente muchos de vosotros tuvisteis la oportunidad de asistir a su preciosa charla sobre micrometeoritos, que también tenéis accesible en nuestro canal del ICE-CSIC, y que, bueno, ha llegado a este planeta para revolucionar nuestro conocimiento sobre los micrometeoritos. Se pensaba antes que los micrometeoritos solo se podían encontrar en la Antártida o en otros lugares, pero evidentemente pues, ha venido a demostrar que en cualquier tejado o zona de desagüe podemos encontrar estas partículas. Y para demostrarlo y hacernos una clase magistral, este señor el 12 de abril pues me acompañó en los tejados del instituto y también de la Autónoma, y muy particularmente pues tuvimos pues oportunidad de hablar y me explicó cosas fascinantes sobre lo poco que lo creían otros científicos cuando decía que había encontrado micrometeoritos en los tejados. Y bueno, pues esto que todavía no... perdón. Esto que ocurrió fue recoger aquí en el tejado del ICE-CSIC esta bolsita con millones de partículas, la mayoría evidentemente de origen antropogénico o terrestre, pueden ser partículas industriales, pero también pues granos de arena, pues material de industria, de condensado, ¿no? En la atmósfera, pequeñísimas partículas micrométricas. Y entre ellas, como él pues con el tiempo y la dedicación ha conseguido pues de estas motas, millones de motas de polvo que había en el tejado del ICE-CSIC, encontrar este que es el primer micrometeorito del ICE-CSIC, y de hecho es uno de los primeros en Europa. Y bueno, se trata de un fragmento de una condrita, y de hecho un cóndrulo de olivino barrado. Aquí tenemos una condrita que ahora voy a enseñar, voy a poner aquí delante, y vemos que las condritas son meteoritos no diferenciados donde abundan esas esférulas que podemos ver. Es como una especie de roca sedimentaria, pero los sedimentos son del propio disco protoplanetario. Y estas esférulas de color blanquinoso aquí, una de ellas, cuando un meteoroide se desintegró en la atmósfera, quedó en forma de este cóndrulo, con ese curioso abultamiento que no es sino un grano de hierro níquel que sobresale de la punta de este micrometeorito. Y por tanto, la textura precisamente es de olivino. Muy bien, pues ahora permitirme, me paso al catalán. Bé, doncs, com heu vist, avui estem presentant aquest projecte de ciència ciutadana en el que tothom està convidat a participar. Evidentment, per una banda tenim, i tampoc per a dir exactament tot el que he comentat abans, però tenim dos projectes principals que són accessibles des de la pàgina web de l'Institut de Ciències de l'Espai del CSIC. Un és aquesta xarxa de bòlids i meteorits, que ja té 27 anys d'història i en la que tenim accés a multitud de registres de molts llocs de tota Espanya i proporcionem pràcticament de manera diària aquest llistat de bòlids i donem una explicació científica, un origen a cadascun d'ells. A més, estem liderant tota una sèrie d'articles de recerca en revistes de primer quartil, donant una explicació científica als bòlids més lluminosos i als esdeveniments, pluges de meteors més importants al respecte. Tenim una sèrie de vídeos també accessibles en la pàgina web de l'ICE-CSIC i també les estacions amb una llista detallada d'aquells col·laboradors que presten el seu temps i la seva dedicació per a tenir registres d'aquests fenòmens súbits, no? I inesperats, perquè són roques petites que no s'observen arribant a la Terra, la majoria de les vegades. Avui dia, gràcies a les xarxes telescòpiques, sí que estem trobant petits asteroides de pocs metres de diàmetre que se troben poques hores abans d'impactar amb la Terra. Per tant, se pot calcular una òrbita preatmosfèrica, però en la majoria de casos, la majoria de caigudes de meteorits són roques de poc més d'un metre o a vegades mig metre, tot així ja són milers de tones, a vegades de la roca incident, i evidentment això es permet, gràcies a aquests registres, tenir una caracterització de tots els fenòmens lluminosos. I a banda, i en particularment esperem una participació d'instituts a Catalunya i també, evidentment, a altres territoris de parla catalana, sobre micrometeorits. Encetem, a partir del pròxim curs, un projecte pilot per a identificar i trobar nous meteorits a les teulades d'instituts de tot el país. I, de fet, el passat mes d'abril, el propi John Larsen, que és un pioner en la cerca de micrometeorits, va estar amb nosaltres a la teulada de l'ICE-CSIC i també d'alguns campus, d'alguns edificis del campus de la Universitat Autònoma de Barcelona, i en particular a l'ICE-CSIC va trobar tota aquesta quantitat de partícules que, evidentment, el gran repte científic aquí és extreure micrometeorits. I és el que ha fet per nosaltres. I aquí tenim el primer micrometeorit de l'ICE-CSIC, que és una còndrula d'olivina barrada amb un petit gra de ferro-níquel en la part superior. Així que, bé, ben aviat donarem molts més detalls sobre aquest micrometeorit i ara passo a la xerrada d'avui. Gràcies a tots els que esteu presents aquí i remotament. Okay. So today is the Asteroid Day. It's a day that we choose and has been recognized internationally because, we were lucky. All the time, humans have been really, really lucky about the impact hazard, asteroid hazard. Why? Because, when you look at every June 30, 2023, in this case, if you know a little bit about impact hazard, then you realize that in 1908, humans were extremely lucky. A huge body, about 30 meters in diameter, between 50 meters in diameter, was disrupting over Tunguska area and was producing devastation of about 2,200 kilometers square of taiga. For just a minor timing difference, few hours, this body could have, for example, impacted over St. Petersburg, producing millions of victims, This was just a lucky event. So in general, this all over the last decades, we have been really involved in trying to increase, the our knowledge on all these phenomena and try to apply our knowledge for direct application. And this is the case of our American colleagues in NASA, in JPL, and the Johns Hopkins University, that were just collaborating with European scientists for many decades, and particularly at the end, waiting for this mission together. At the end was just NASA decided to move for directly into this DART mission. Finally, the European Space Agency achieved to be granted for doing ERA mission. But as you probably know, this started many decades ago, and we were just behind a double mission in which ERA should be over there in the Didymos binary asteroid. This wouldn't achieve, but you know, scientists have ways to make history, and this is the case, and we need all to congratulate and to thank this extraordinary cooperation, international cooperation. Without that cooperation, never this achievement could have been obtained. First of all, I will say, well, we really know what is the big deal of all these studies of asteroids, because sometimes people say, well, that has been the first you know, planetary defense mission. That's wrong. There have been many planetary defense missions, perhaps not directly related, but every time that we send a spacecraft to the close by, you know, some of these bodies, asteroids, comets, we are learning many things about their content, the composition, the structure, and of course the properties, because this is a huge challenge. We are talking that planetary defense is just trying to deflect asteroids, but we have big questions over here, because asteroids, most of these asteroids have been here surrounding the sun before the Earth was formed. Many of these asteroids have been suffering catastrophic collisions at a degree that almost most of them are rubble piles. So you can imagine, here we have two different scales. On the right, on the left in the screen, we see, for example, bodies that are about 100 kilometers or smaller. And then we have over the right these asteroids that are bigger. And we can see in particular Lutetia, that was visited by Rosetta spacecraft before visiting 67P Churyumov-Gerasimenko comet. And we can see with the arrows what is the real size compared with Vesta, that is one of the biggest differentiated asteroids that have been melted internally. But most of these asteroids are just you know, legacy of the creation, because they have been never melted. They have been never bigger than 100 or few hundred kilometers. So they are made of the chips, the small rocks and materials that were surrounding the sun in the protoplanetary disk. So understanding and studying these meteorites, undifferentiated meteorites in particular, that are reaching the Earth, and we are collecting with these sample return missions, is of the first scientific interest. Why? Because we can collect you know, direct information of the composition, structure, and properties, chemical and physical properties of these materials. So as you can imagine, to deflect asteroids, is a big scientific conundrum, in the sense that we need to deal with many factors. What is the structure of this body? What is the composition? What is the size? And these are details that we don't know. When an asteroid is approaching to Earth and we have, for example, hours or days to impact, we really need to focus in the real important things. And that's why that has been conceptually the key. I will talk a little bit about that. In any case, here is the accumulated number of asteroids. In order to explain, over 1,000 kilometers in diameter, we talk about planetary bodies. All the asteroids are smaller than 1,000 kilometers. The biggest is Ceres, that is almost in the size of 1,000 kilometers, a little bit less. And then we see that there is this logarithmic decreasing numbers that in fact are telling us that they are hundreds of millions of asteroids with diameters that are a few hundred meters, in general. So this is one thing that this is the accumulated number of asteroids. What are the asteroids made of? We know really a huge diversity and complexity. Sometimes bodies have been colliding with each other, so they are, mixtures of different types. But in general, we can find rocky irons, and also challenging fragile aggregates that are extinct comets, like, for example, has demonstrated Hayabusa 2 JAXA, Japanese agency mission, that has been bringing to the Earth, to our labs, materials of this Trigo asteroid. At the same time, NASA mission will bring very soon, hopefully, materials of another extinct comet, asteroid Bennu. So these are fragile aggregates that increase still the challenge of deflecting this type of bodies, because they are so fragile that probably putting them close by the Earth could be disrupted into pieces, small pieces. This was another historic mission, Hayabusa, that achieved to study this rubble pile asteroid Itokawa, and the small chips of the regolith were brought to the Earth, and we were lucky to study these chips in the Institute of Space Sciences in our clean room of meteorites and sample return missions. And well, where are these the asteroids coming from? These are continuously reaching the Earth, mostly from the main belt, also these rocks that are producing meteorite falls. In general, we have all these asteroids, in surrounding the sun. Mostly are located in this main asteroid belt that is between Mars and Jupiter. But there is a continuously scattering of bodies because of planetary resonances that are bringing these asteroids to near Earth space, where typically they can stay few millions of years until getting back to the main belt. So it's a continuous flux of incoming and outgoing materials in this, in the case of these asteroids. We know 853 asteroids of this category that we call near-Earth asteroids, with a diameter larger than 1 kilometer, and about 32,000 in total. plus about 121 comets. And then we have potentially hazardous asteroids that are defined as bodies that are larger than 150 meters and with a minimum intersection distance. No, the orbit of this asteroid with the orbit of the Earth is approaching as minimum about 7.5 millions of kilometers. In total, we know of this category of potentially hazardous asteroids 2,342. And between 80 and 90% of these bodies are coming from the main belt. Oops. The reason is just what we know as planetary resonances. Mainly in the inner part of the main belt, we have the gravitational interaction with Mars, that is a small planet, but really close by the inner main belt is producing many planetary resonances. Of course, Jupiter, that is altering many places in the asteroid belt, and that's the reason for these discontinuity lines that are known as Hilbert gaps. Okay, and then we also identified other type of resonances that are called secular resonances, particularly with planet Saturn, that is also forcing the asteroids that are crossing these heliocentric distances to move away and change the eccentricity and the parameters of the orbit to become, for example, Earth crossers. Okay, just to focus a little bit more, then let's explain briefly the main goals of the DART missions. These were the requirements. First of all, of course, impact Dimorphos. That was already a big challenge and achieved thanks to hundreds of mechanical, electrical, computer people that has been working for years, and John Hopkins University and also NASA, JPL in this mission. They managed to get a spacecraft absolutely amazing, able to work alone and direct and going directly at hypervelocity, reaching with these ionic motors 6.1 kilometers per second, and even when the spacecraft was only a little bit more than 600 kilograms in mass, achieving the result I will explain later on. Because originally the second point in here, the requirement was we have this binary set of asteroids, Didymos, that is 760 meters in diameter, and Dimorphos, that is about a little bit less than 160 meters in diameter. And the Dimorphos is just rotating and orbiting the main body. The original idea was impacting Dimorphos with DART and decreasing the orbital period of Dimorphos around Didymos in at least 73 seconds. Then, of course, another big challenge in which were involved ground-based telescopes, but also space telescopes, was, observing these two bodies that, in fact, photometrically are only one, studying the changes in the photometric behavior because of the movement of the secondary surrounding the primary. So you have a photometric curve, and from this photometric curve, being able to quantify the change in the orbital period of Dimorphos. Okay, this is another big issue. And then, obviously, the fourth requirement was measuring the parameters that is called beta. That is the factor in which, you are contributing to deflect the asteroid. I will, in next slide, explain this. It's called the momentum enhancement factor. Excuse me. Trying to deal. Okay. So the implications for crater excavation and transfer of kinetic momentum from a probe to an asteroid, this was the main goal, no? Trying to deflect an asteroid in an efficient way and can be measurable from space. We consider to increase the momentum transfer to Dimorphos this multiplication factor, the beta factor, where we can see here how the spacecraft is colliding with the asteroid, and then you have the different components. Perfect. I was trying to do so. Okay, so the term that you have on on the upper part of the equation, you see that that represents the transfer of the direct momentum, and here is the P sub E represents the amount of momentum that is provided by the ejecta, the amount of material that is escaping in the impact plume. If you throw the projectile against the asteroid surface, you have a contribution that is very relevant of this ejecta that is going and is increasing in a natural way the effect of the impact. That was a kinetic impactor, so was not containing any kind of explosive charge. Just using the kinetic momentum to hit the asteroid, producing crater excavation and throwing as much as possible materials in opposite direction. In fact, we were working in the Institute of Space Sciences for years, trying to develop a technique with meteorites that is the nano indentation. Thanks to our collaboration with Jordi Sor, researcher at the Autonomous University of Barcelona, we were the first in applying this nano indentation technique to understand and to quantify the mechanical properties of regolith. And I think that we were able to make a significant contribution. And what was amazing is finding at the end of all this process that DART was able not to decrease the orbital period of the Dimorphos in 73 seconds, but doing it for 33 minutes. That huge achievement was also by the fact that Dimorphos is a huge amount of appulated rocks, So I will talk about that in next slides. In general, they are many other people. We could stay here for hours citing people, but Patrick Michel numerical models were able to just quantify most of this effect, and particularly George Flynn experiments impacting at hypervelocity in laboratories, not at so high velocity, but at kilometers per second, few kilometers per second, in using these accelerator guns, were able to get very significant information about the behavior of these materials. So the mission, you should look, if you have not yet seen the approach captured by Draco camera. The only instrument in this DART mission was one camera. Obviously, you have a lot of sensors, but only one camera, and all the processing of the images and all redirection of the system was made in situ in the spacecraft, with not direct intervention. So that's a really amazing achievement for people in NASA, JPL, and Johns Hopkins University. Just also think, as you see, this just 4 frames of the sequence taken by Draco, that is on the left of the image. You see first, in the first image, Didymos and the tiny Dimorphos at this distance. Then was identifying that the target, obviously, always there is a trembling, a movement, a trembling in the camera sensors, and then automatically it was pointing to the small target, going to Dimorphos, and finally hitting the asteroid. This was almost the last image where DART impacted. And as ERA was not flying yet, because European took more time to decide about the interest of this mission, finally ERA will fly. But we were the contribution of really smart Italian colleagues that brought with DART a CubeSat. And was the first time that in interplanetary space was operating a CubeSat that was called Lycia Cube, that allow us, people from ASI, to get this incredible image where we see Dimorphos impacted by DART with this impact plume and Didymos below it, with the sunlight increasing at first. And just using all these Draco camera images, this has been the picture of Dimorphos. Probably you like the Pyrenees or the Alps. You have been climbing for sometimes over there. Well, just thinking, bringing with you a bag of 160 meters, and then try to collect as much stones as possible, and of these stones, those that have cutting edges, the most complicated stones. Put all of them in a bag 160 meters in diameter. Bring these to a space, and then in a space far from the Earth, hopefully, throw them up. And then you will have Dimorphos. Then imagine how huge challenge is deflecting an asteroid like that has been, disrupted to the level that is just a rubble pile. And just think that in the past, most of these asteroids that have been impacting the Earth, probably the same impactor that made the Tunguska event was like this. In fact, there is some possibilities that the Tunguska impactor was a piece of a Encke comet. So I will explain that later, but quite interestingly, we were as well observing the effects on Didymos system of that impact. A team collaborating with us from the Instituto de Astrofísica Andalucía, also CSIC, led by Alberto Castro Tirado, was obtaining a very nice sequence where we can see on top right the image taken the night before and the night after the impact, where we see the significant increase in the magnitude of the binary asteroid. And then using our collaboration with Pujal Observatory and a smart guy that is called Josep Maria Llenas was providing us very, very nice, exciting pictures of the dust trail. And you see, let's see if I can put this. Here is Didymos, and in the original image, you can see the dust trail going over the image. So we are almost reaching the end of the talk, but let's go back to Tunguska. You know, we were thinking that perhaps the biggest hazard due to asteroid impacts is you know, like the hazard described in the movies, but probably is not. Because most of these asteroids, most of these potentially hazardous asteroids, we know now, thanks to all these space missions, particularly sample return missions that are bringing materials to the Earth, that are rubble piles. And rubble piles behave like we didn't know objects that are specifically disrupting in the atmosphere, not producing craters, but producing huge devastation over thousands of kilometers square areas. And that's a very important learning from all these things. As I said at the beginning, Tunguska happened in a very remote Siberia peninsula area, but for about 6 hours of difference could have been falling against a really populated area. And then perhaps suddenly at some point, that time it didn't happen, but could be happening in the future. And that's why people understanding asteroids and comets, we are trying to promote the interest for all these phenomena, because you know, the consequences for all these impacts probably can be palliated in a very simple way, just deflecting asteroids before it is too late. It is important to say that, you know, European Space Agency has a planetary defense office, as well NASA and JPL has the Center for Near Earth Object Studies, CNEOS, that provides a really updated table for impactors in the next centuries, where you can easily reach the information about what is the, you know, probability of impact. And in all cases, for centuries and for, I would say, thousands of years, there is no risk at all because the probabilities are really small. At least of those asteroids that we know. But still, we miss a significant fraction of asteroids smaller than 100 meters. And that's the big deal. We need to find these bodies, and we need international cooperation probably to put in orbit infrared telescopes that are able to find these asteroids, track them, obtaining their orbits, and being able from all this information to make a real important forecast just to avoid the next Tunguska event. Because the asteroid impact consequences could be really devastating. When we are talking about bodies a few hundred meters in diameter, we can say already that could be impact crater excavation, production of tsunamis and energy transport in case that these asteroids fell against the sea. Of course, all these materials that are thrown to the atmosphere suddenly produce global darkening consequences due to this dust and smoke that produce fast climatic change consequences, direct consequences on agriculture, livestock, farming, fishing on a global scale. And of course, injection of huge amounts of oxygen to the atmosphere, because most of these bodies are silicates containing huge amounts of oxygen. And these silicates are preferentially ablated in the atmosphere and vaporized. So this could produce, associated with an impact plume, huge fires over this area in which the material, the incandescent material, is falling. And of course, poisoning the entire biosphere just by injecting huge amounts of sulfur. Don't forget, for example, that you have a lot of sulfides on these materials, like troilite grains that are typically associated with iron nickel alloys. Also sodium, because we have plagioclase and other minerals that contain sodium, and the same materials in comets are enriched in sodium, chlor, phosphorus, and other substances. You know, and then let's see. Let me move on. In general, I will transmit really. We should be calm. No, we don't need to open, you know, news every day and hearing about impacts happening by asteroids and, you know, this forecast that doesn't make sense. We already know this is a very well message for journalists. We don't need to claim that there is an impact every month because there is not. But we need to explain people that every few centuries we have bodies that could be in the size of Tunguska. Over thousands of years, we could have bodies that are larger. And then, of course, it's not a direct worry right now, but it's important to, you know, catalog of all these bodies and be able to predict their movements. And of course, explain also to the people that these huge catastrophes, like, for example, that one, this 12 kilometers diameter body that produced the change of era, no? Let's say about 65 millions of years ago, with the destruction of all the dinosaurs environment, is happening over time scales of tens of millions of years. So it's not something we need to worry. All these kilometer-sized asteroids reaching, passing close by the Earth are known, and we have not hazard associated with them, and we need to, in that sense, be relaxed. These are some of the reviewed publications, the different articles in Nature we have contributed with our DART mission colleagues. We were forming part of the investigation team, and it has been one of the most beautiful experiences for me, together with the participation in the Stardust mission also of NASA. And we are really excited because more papers will be coming. They are really fantastic colleagues in mission. In this mission, working in many topics that are of interest. I also put all my effort last year in bringing this new book in 3 languages. Was a big challenge for me as well. You know, first Asteroid Impact Risk, then La Tierra en Peligro y La Tierra en Peril, in which, you know, I try to make all these phenomena accessible to everyone, trying to understand why this is important, why the scientists we need to bring all these ideas to the population, as the same Asteroid Day does, in the sense that the Asteroid Day is an initiative all over the globe to popularize the interest of studying asteroids, comets, and all these meteorites. So thank you. Please keep watching and protecting the dark sky, because the dark sky link ourselves with our cosmic origins. I see, you said? Okay. It's because it's you know, has the characteristics in which have been you know, every one of these spherules can be characterized, it can be obtain the chemistry that is peculiar in this case of a chondrite. This is the typical bar olivine condyle that we can find in an ordinary or carbonaceous chondrite. In particular, also has a small, you know, bunch of iron nickel alloy in the peak. So it's really easy to identify. Easy not, but the composition and of course the structure itself. The overall structure is characteristic of one of these small, you know, globules that are, you know, glass spherules that are forming chondrites, that are undifferentiated meteorites. So this spherule we found on the roof of the ICE was flying, surrounding the sun, you know, about 4,567 millions of years. Was just going through the sun, and then was colliding with other condyles, and then forming an asteroid probably. But at the end, the entrance of the meteoroid in the atmosphere was fracturing the body, and only few of these fragments were surviving. One of them found in our room. Welcome. Well, exactly. This Italian CubeSat was detached from the main DART few weeks before, the impact, and then has been obtaining images since then of the system, and then being operated in deep space for a while. Yes, also very important mission in that sense for CubeSat concepts as well.
I understood that you found
Well, typical micrometeorites are in few microns to tens, few hundred microns in general, and this is in more or less in the middle. It's not trivial to and a magneto. Magneto is an important. We can collect also, they are some, of course, no magnetic, but the magnetic are easier to be found. Yeah, but of course you have a lot of particles from the Earth, many processes in the Earth that produce magnetic particles. Particular industrial processes produce smokes that recondense into magnetic particles as well. So you need to be patient. I can assure you.
Any other question? No? I think we have
Good. Just remember that tonight, if you are interested in this talk in Spanish, el Planetario de Bogotá pues nos lo va a ofrecer en primicia, y bueno, agradecer y saludar a todos nuestros amigos en Latinoamérica, también muy contentos de haber caracterizado los primeros meteoritos también de nuestro grupo en Argentina y en Colombia, ese meteorito Cali, y bueno, será un placer pues veros a muchos de vosotros y que os pueda explicar esto también en castellano. Thank you very much, everyone.